This conference will now be recorded.
Good afternoon, one and all. This is Rajesh from EC department. So our subject is embedded system design. As we covered in our previous video, elements of embedded system. So these elements of embedded system is consisting of the sensors, actuators, system core, the core of the embedded system, and memory, then the peripheral devices. So our topics are core of embedded system. So we have seen it is a general purpose or domain specific. So under general purpose processors, the core of the embedded system, if you see, the core of the embedded system is a general purpose. This general purpose can be a processor, microprocessor, microcontroller, or a digital signal processor, or it can be an ASIC, application specific integrated circuit, or it can be a PLD, programmable logic device. It can be a programmable ROM, it can be programmable PLA, or it is PAL, programmable logic array or programmable array logic. So this PLD, it is a simple PLD. You can design it as a complex PLD as CPLD, or you can go for another architecture as FPGA. So your system core can be a general purpose like microprocessor, microcontroller, DSP, or it can be an ASIC, or it can be a PLD, or it can be a commercial off-the-shelf component. So commercial off-the-shelf component means it is readily available. It can be manufactured. It is manufactured by the manufacturer, and you can just use the single like TCP/IP unit or any remote controlled control unit used in an electronic toy. You can purchase from the vendor. You can directly insert in the embedded system. So this system core is getting the inputs from input ports, so which are connected to our sensors. Sensor is a transducer device which will detect the input of any variable, and it will convert in an electrical signal, and it will send again, it is converted to a digital signal by A to D converters, and it is the data is sent to your system core, and system core output is connected to output ports. This output ports will control the output devices by an actuators, and this system core is connected to the memory, and the data is bidirectional. So your instruction fetching, execution, and again data storing is done in the memory. So this for this there is a bidirectional thing, and some other devices like push buttons, keypads, all are connected to your this system core. So elements of embedded system will tell the block level. There is an input port sensor, output ports actuators, memory. This memory is getting the contents as application software called embedded firmware that is stored in the memory. And all sensors, actuators, memory, they all are connected by an interface called communication interface. This can be an onboard or offboard. That is called onboard. It is related to the PCB, how these sensors, memory, system core, output ports, sensors, actuators, they are connected. That is called onboard. Offboard means that is external to your system core. So coming to our, so if this Arduino board is having one LED relays, light sensors, temperature sensor, infrared receiver, buzzer, potentiometer. So communication interface. Communication interface is essential for communicating with various subsystem of the embedded system with the external world. The communication interface can be viewed into two different perspectives. One is device or on board level, that is called on-board communication interface. So we can classify it as device or board. The other name is on-board. The second one is product level communication interface. It is called external communication interface. So product level is called external communication interface. Device level it is called on-board. For any embedded system, the communication interface is classified into two types: onboard communication interface. So this is the communication occurring between the different components present on the system. Examples are I2C. I2C means I2C, inter-integrated circuit, serial peripheral interface, SPI interface, UART, universal asynchronous receiver transmitter, one wire interface, parallel interfaces. So these interfaces are like nothing but a bus having the architecture of one of these interfaces connecting the components of your embedded system. Product level communication interface or external communication interface. Product level communication interface or external communication interface. The product level communication interface is responsible for transferring the data from the embedded system to other devices or modules. And this interface can occur either wired or wireless media, and you can transmit the data either serially or parallelly. So for under wireless transmissions, an embedded system can send the data using wireless methods using infrared techniques, Bluetooth, wireless LAN, Wi-Fi, radio frequencies, RF or GPRS. Next, wired interfaces. So under wired interfaces, an embedded system can transmit the data using a port called IEEE 1394 port, RS232C, RS422, RS485, or USB, Ethernet, TCP/IP protocols, or parallel port. So these are the wired interfaces from the embedded system to the external world. So if you see this diagram, an house is having various sensors and actuators. We are having fridge sensor, door window protection, carbon monoxide detectors, personal emergency, motion detector, smoke and heat sensors, keychain touchpad, and water sensors. So many sensors will be connected to an house. So these sensors can transmit the data wireless. So onboard device level communication interfaces. The communication channel is going to interconnect the various components of embedded product, and the buses used are these are I2C, inter-integrated circuit bus, SPI bus, next UART, one wire and parallel interfaces. So first one, inter-integrated circuit bus, is pronounced as I2C. So within the embedded system, this hardware, the system core can be a master, the memory can be a slave, or sensor is transmitting data to the system core, or system core is transmitting the data to the actuator. So this all are connected as master slaves by using a bus called inter-integrated circuit bus, which is a synchronous bidirectional half duplex. Half duplex means one direction communication is occurring at a given point of time. So from the system core to memory or memory to system core will occur, but at a time only one directional communication will occur. One directional communication at a given point of time will occur. So this is a synchronous bidirectional half duplex two wire serial interface bus. So the data is transmitted serially. We'll be having two wires, one wire for synchronous clock, another for data, and it is bidirectional. Both way data can transfer, but it can occur only half duplex. At a time only one communication will occur. So this is originated by Philips Semiconductors in early 1980s, and it is an easy way to communicate between microprocessors and the peripherals in televisions. So coming to architecture, there is a master. It has some ports called SDA and SCL, and the bus is having two wires, and each of your slaves and master will have this SCL and SDA connected, and they are synchronous. So here in this SDA and SCL connected to microcontroller, EEPROM, microcontroller, ADC. So as you told, it is comprising of two buses, serial clock, SCL, serial data, SDA. This SCL is generating synchronous clock pulses. SDA is transmitting the data serially across devices. It is a shared bus system, and either anyone can act as master, the other will act as a slave, and devices acting as slave will wait for the commands from the master and respond to the commands. So there are the sequence of operations you can communicate between master to slaves under I2C, I2C communication. So master device will pull the clock to high, and master device puts the data and keeps a low, and master sends the address of the slave device to be communicated. These clock pulses are generated on the SCL, are synchronous, and the MSB of the data is always transmitted first. Data is valid during the high period of the clock. In normal data transfer, data line only changes state when clock is low, and master waits for the acknowledgement bit from the slave whose address is sent. So once the address is sent, one of the slave devices will send the acknowledgement. So this is the data format of MSB to LSB, 7-bit slave address. So there is R by W. So if it is R0, master is writing to the slave. If R by W bit is 1, master is reading the data from the slave. ACK is the acknowledgement bit generated. So this is the data communication. How SDA and clock, how data is transferred along after slave is detected to that slave, data will be transmitted in bytes and the acknowledgement bit is sent. So the second type of communication is serial peripheral interface bus. Serial peripheral interface bus, SPI bus, is also synchronous, bidirectional, but compared to I2C, it is full duplex, and it is having 4 wires. So what is this full duplex means? At a time, both communications can occur, and it is having 4 buses. It is implemented by Motorola. It is a single master multi-slave system. So here only one master will be there. All the devices will act as slaves. So SPI is used to send data between microcontrollers and peripherals, and using such as shift register, sensors, and SD cards. So each of the devices will have one S clock, MOSI, MISI. So the 4 wires are MOSI, master out slave in, MISO, master in slave out, serial clock, S clock, SS, slave select, SS. So MOSI stands for master out slave in, the signal line carrying the data from master to slave device. So it is because it is carrying the signals from and data. This is the signal line carrying the data from master to slave. All the devices will be connected with these 4 lines: MOSI, MISI, serial clock, and a slave select. Once slave is selected, it is an active low signal. The master will generate a synchronous clock signal, and it is trying to identify the slave. Once slave is identified, so data is transmitted from the master to slave. So that is called, it is other name is slave input or slave TI. Similarly, master and slave out. So data is transmitted from the slave to the master. So that's why it is called slave out. So the size of the shift register is device dependent. Normally it is a multiple of 8, and all the master slave devices will contain a shift register and a buffer register. So they are connected synchronously by all this MOSI, MISI, and S clock. Based on the master to slave, slave to data transmission will occur. So each will have the memory. S clock is synchronous between master to slave, and MOSI means master out to slave in, MISI means slave out to master in. So the next type of interface on the board is one wire interface. It is a device communication system designed by Dallas Semiconductor. It is transferring a low speed data signaling method and power over a single conductor. So it is designed by the Dallas Semiconductor and providing a low speed data and power over a single conductor. So all lower data rate, lower range, such type of devices such as digital thermometers, weather instruments, you can use this one wire interface. The distinctive feature is it is having a data wire and a ground wire, and it includes a 800 picofarad capacitor to store the charge and to power the device during the periods when data is active. So there is always one master in overall charge, which can be a personal computer or which can be a microcontroller. The master initiates activity on the bus, and protocols are built to detect the collisions. If a collision is occurring, the master will do the communication again. So many devices can share the same bus. Each device on the bus has a 64-bit serial number. So slaves have the 64-bit serial number. The least significant bit of this serial number is an 8-bit number that tells the type of device. Okay, so the master starts a transmission with a reset pulse by pulling the wire to 0 volts for 480 microseconds. So it starts the transmission by sending a reset pulse for 480 this resets every slave on device, and if any slave device if present, it exists a presence pulse by for up to 60 microseconds, and to send a 1, the master bus sends 15 microseconds lower pulse. To send a 0, the master sends a 60 microsecond lower pulse. So while receiving the data, the master starts sending 15 microsecond 0 volt pulse to slave device. So like this, a protocol is used and the devices are identified by 64-bit serial number. So in this diagram, the one wire master is connected to all the slaves using one wire logic. The next type of communication is parallel communication. In data transmission, we can also use onboard communication, a parallel communication where multiple binary bits are simultaneously transferred. This communication channel is having a number of electrical conductors used at the physical layer to convey the bits. This parallel communication implies more than one such conductor. If you consider 8-bit parallel communication, it is having 8 bits transmitted simultaneously, whereas serial communication means 8 bits will be transmitted one after another. And it is widely used parallel communication, and most peripheral buses, memory devices, they go like this. So here two sender and receiver are transferring data on a 8-bit buses. So data will flow on each bit 0 to bit 7. So under onboard or board level, we are covering 4 types of buses. So these 4 types of buses are, like we have covered. First one is I square C, next one is SPI, and next one is one wire, and the next one is parallel. So these all come under onboard. Onboard means the master is your processor and peripheral devices are devices on the board. Product level or external communication interface is nothing but your embedded system is transferring the data to some other portion of your embedded devices placed at a remote area, and this can occur by 2 methods. One is wired communication interface, another is wireless communication interface. What is wired communication interface? Wired means you have to transfer the data over a wired network. So for that we are having different examples, but if you are going for wireless, means they can transfer by using some protocols. So under wired communication, so your personal computer or hardware system core is, or your total embedded system is transferring the data by wired technique. You can use RS-232 or RS-485 or USB universal serial bus or IEEE 1394 firmware. So these three are wired communications. If your embedded system is connected to any display unit, by using these methods, you can transfer the data. Wireless means embedded system is transferring the data by any wireless methods called using infrared rays, Bluetooth, Wi-Fi, Zigbee, or general purpose, general packet radio service. It is GPRS, general packet radio service. So coming to first one, wired communication, product level or off board. RS-232, it is a 232 is a standard number 232. C is the version number from EIA, Electronic Industry Association. It is a full duplex wide communication, but it is an asynchronous serial communication interface. So full duplex means at a time both master to slave, slave to master communication can occur by using a wide one. Means separate ports are provided for data transfer. It is asynchronous and data is transmitted serially. So it is extending the UART communication signals for data transferring. UART is using standard TTL logic. Logic high corresponds to bit 1, logic low corresponds to bit 0. So RS-232 is, it's a standard. As per EIA standard, a logic 0 can use a voltage between plus 3 volts to 25 volts, and a logic 1 is represented with minus 3 and minus 25 volts. So anything voltage lying between minus 3 to minus 25 volts is treated as logic 1, plus 3 to plus 25 is treated as logic 0. And another terminology is logic 0 is called as a space, logic 1 is called as a mark. So this communication is occurring by various handshaking and control signals occurring between transmit and receiving receivers for data communication. This RS-232 is separate, covering two types of connectors. You can have a DB9 connector or DB25 pin connector. So if you consider the 9-pin connector, the ports are 9 pins. One is DCD, one is RX, one is TX, one is DTR, GND, DSR, RTS, CTS, and RI. So DB9 connector is having this all specifications for 9 pins, and similarly DB25 is having also 25 specifications. So this RS-232 is a wide asynchronous serial full duplex communication developed by EIA in early 1960s. It is extending the concept of UART, and we are using the voltages for plus it is minus 3 to minus 25. For logic 0 it is plus 3 to plus 25 volts. So if you go into the interface, RS-232 is a point-to-point communication. It is full duplex, and the devices connected are termed as two names. One is called data terminal equipment. The other device is called data communication equipment. So if two devices are connected by RS-232 port, the one device is called DTE, another device is called DCE. That transmit pin of one DTE is connected to receive pin of DCE. Similarly, receive pin of DTE is connected to transmit pin of DCE, and both grounds are connected. Like personal computer to, if modem data exchange is occurring, transmit is connected to receiver, receiver is connected to transmit pin. If no data flow is required, these transmit and receive signals and ground are only required. If any data exchange is occurring other than this, we can use some other control pins. So what are they? The control signals implemented for modem communication to the personal computer are RTS, request to send. So RTS stands for request to send, CTS clear to send signals between DTE and DCE. So DTE and DCE are the two terminal names used in RS-232 communication. So RTS stands for request to send, CTS stands for clear to send. When DTE has data to send, it activates the RTS line. So RTS means request to send. And if DC is ready to accept, it activates CTS line. So if it is ready to accept, the DCE is going to activate the CTS line. CTS means clear to send. So upon seeing clear to send, the DTE will transfer data from DTE to DCE. And data terminal ready is activated by DTE when it is ready to accept data. So if you want to send the data, it will use RTS. If it is wants to receive the data, it will use DTR, data terminal ready. Similarly, if DCE is ready to send the data, it is uses data set ready. Other than this, there is a data carrier detect used by DCE to indicate the signal received is good. The data received is good. So this RS-232 is also using one more pin called ring indicator for indicating incoming call on the telephone line, and the data rate is called a baud rate up to 20 kilobits per second. And you can design the RS-232s of different baud rates, 300 bits per second, 1200 bits per second, to maximum of 19.2 kilobits per second. And the operating speed is within 50 feet. It is also using UART standard, and it is equipped with MAX 232 level translator IC for communicating data between UART to RS-232. So under wired interfaces, off-board product level or external communication interface, first one is RS-232. Second one is USB, Universal Serial Bus. This Universal Serial Bus is an external bus standard. It is allowing connection of peripheral devices to your embedded system, such as keyboards, scanners, printers, joysticks, audio devices, and the transfer of data rate is occurring is 480 megabits per second, and this is for USB 2.0. So depending upon USB selected, this data rate will vary, and it is developed by Intel, Microsoft, Compact Deck, IBM. It is a low speed device. Signaling rate is 1.5 megabits per second. Full speed data you can use, and for high speed it is 400 megabits per second. So the connector is using a serial A cable connecting USB devices to hub ports. Another series B cable is connecting detachable devices. So how these are created is you can follow a bus topology. So in bus topology, the root hub is connected to the all functioning devices by using a bus topology, where you can connect various parallel and serial ports. You can use the star topology, and it will allow maximum of 127 devices using USB connection. And if USB is used for your wired communication, USB host device controls all the peripheral devices, and it will test status information of all the child devices, and it acts as a repeater, boosting the strength of coming and upstream and downstream signals. So that is under wired communication for product or external interfaces. So embedded system communicating to external world using either RS-232 or USB. If it is following a wireless technology means an embedded system will transfer without the help of any cables or wires to an external world. So that can occur by various methods called infrared, Bluetooth, Wi-Fi, Zigbee, and general packet radio service, GPRS. So first one is infrared. Infrared is a certain region of your light spectrum. It is ranging to 0.7 micro to 1000 micron. It is broken into near and mid and infrared. So this IR transmission means there will be a transmitter and a receiver. The data is transferred as an IR signals. So this there will be a transmitter at the IR LED, so which emits infrared light for every pulse. So depending upon the electrical pulses, this LED will emit a wavelength of 940 nanometers by using a series of pulses corresponding to the button pressed. If there is an on button, it will send a specific pulse. If there is an off button, so data is in terms of written in terms of button pressed. So that data is transferred as a infrared rays corresponding to wavelength of 940 nanometer. And this is used for benefit of human beings, light bulbs. Uh, but because the human beings cannot identify infrared signals, and the signal is weak, we can also use go for modulation, where transmitted signal is modulated by a carrier signal of 38 kilohertz, and this IR LED is made to oscillate at this frequency, and the information or the is passed on to a light and modulated at 38 kilohertz frequency. This IR supports data rate ranging from 9600 bits to 16 megabits per second. If you are using serial infrared, it is 9600 bits per second to 115.2 kilobits per second. Medium infrared, 0.5 megabits per second to 1.152 megabits per second. Fast infrared, 4 megabits per second. So there you can see a transistor at the collector side. We are placed an infrared LED. So based upon the input pulses, so there is a button pressed on pulse, off pulse. It is generating one infrared signals, which is detected at the infrared receiver by one more IR receiver, and it is generating the output signals in the same way. So coming to this, next is Bluetooth. Bluetooth is a wireless technology for short distance communications such as mobile devices, PAN, personal area networks. So it is developed by vendor Ericsson 1994. It is an alternative to wireless services similar to RS-232, and it transmits data at using a channel as a bandwidth of 1 megahertz. This Bluetooth uses a radio technology called frequency hopping spectrum, and data is transmitted in terms of packets, and each packet transmit each packet on one of the 79 designated Bluetooth channels. Each channel is having 1 megahertz bandwidth, and it performs 800 hops per second with additive frequency hopping enabled. And the modulation used is Gaussian frequency shift keying modulation. Now, because of introduction of Bluetooth 2.0, we can also use pi by 4 differential quadrature phase shift keying or 8 DPSK modulation between compatible devices. So as we have listened, Bluetooth is a packet-based protocol. From master to slave, packet will be transferred and to the 879 designated Bluetooth channels, and each channel will be allocated 1 megahertz, and data rate is selected to be 800 hops per second. The data is transmitted the usual hops and with the additive frequency hopping. All devices share the master's clock. Packet exchange is based on the basis clock defined by the master. So next wireless technique, product level or external communication interface is Wi-Fi. Wi-Fi, as it is named, it is a wireless fidelity, wireless LAN. It is used for all high-speed internet connections. It is following IEEE 802.11 standard. It supports internet protocol-based communication, and it requires one Wi-Fi router access point to manage the communication. This Wi-Fi router is responsible for restricting the access to the network, assigning the IP address to the devices on the network, routing the data packets to the specific devices on the network. So the main core of this communication is Wi-Fi router. So if you see the wireless home network, there one router is connecting to a modem, computer, smartphone, tab, and they are all communicated through an internet. And it is following the protocol is Wi-Fi. This Wi-Fi enabled devices use a wireless adapter for transmitting and receiving data at speed of 2.4 gigahertz or 5 gigahertz of radio spectrum. This Wi-Fi network is identified by a SSID called service set identifier. So whatever the Wi-Fi communication you create, that communication is having identified by one service set identifier. To this service set identifier, all the devices in the network will be connected. So you will follow, you have to attach to this SSID, and for security purpose and for authentication data transfer, it is also having wireless equivalency protocol or wireless protected access for security mechanism. So the next wire technique is Zigbee. Zigbee is an IEEE 802.15.4. So it is IEEE 802.15.4 based specification for high-level communication protocol used to create personal area networks with small, low-power digital radios such as home automation, medical device data communication, low bandwidth, small scale projects where you require wireless communication. Zigbee is a low power, lower data rate, close proximity, wireless ad hoc technology. The technology is defined by some specifications where you also use this simple designs compared to wireless personal area networks or Bluetooth or Wi-Fi. The applications of Zigbee include wireless light switches, electrical meters with home displays, traffic management systems, consumer, industrial equipment, short range, low rate wireless data transfer, and the transmission distance is 10 to 100 meters, line of sight, so depending on the power output and environment characteristics. If you follow mesh technology, this Zigbee can be used for long distance communications. So this Zigbee has a Zigbee router which is connected to the devices Zigbee any device by a star network, and this network is connected to another network by using a Zigbee routers, and the main coordinator this controlling the mesh network is called Zigbee coordinator. So Zigbee coordinator is connected to Zigbee routers. Zigbee router is connecting one mesh network to another mesh network, and each mesh network, all devices like Zigbee router and Zigbee coordinator will be connected by a mesh network. This mesh network connects one star network to another star network. So Zigbee coordinator acts as the root of the Zigbee network. He is responsible for initiating the Zigbee network, and it has the capability to store information about the network. Zigbee router is responsible for passing the information from device to another device. So end device containing Zigbee functionality for data communication. It can talk only with ZR or ZC. It does not have the capacity for mediating, transferring between one device to another. So it is supporting a distance of operating distance of 100 meters at a data rate of 20 to 250 kilobits per second. So next wireless method. So this is onboard or external communication interface where embedded systems are communicating with the external world using infrared, Bluetooth, Wi-Fi, Zigbee, or general packet radio service. So this general packet radio service is called GPRS. It is a packet oriented mobile data service on the 2G and 3G platforms for mobile communication. This GPRS is having standardized by European Telecommunication Standard Institute. It typically charged based on the volume of data transferred, it contrasting with circuit switched data, and billing time is broken down to every third of a minute. Usage above the bundle cap is charged per megabyte speed limited or disallowed. And the services offered is GPRS extends the GSM packet switched data capability and makes the following services: SMS messaging broadcasting, always on internet services, multimedia message service, push to talk over service, instant messaging and presence wireless internet applications, point to point, point to multi-point. So these are the services of GPRS. So coming to our topic, elements of embedded system, we are having a sensor to detect. It is a transducer which converts physical quantity of any type into electrical signal. Actuators, electrical signals to physical actions. These are connected to your core. That core can be any hardware, general purpose, or ASIC, or PLD, or COTS, commercial of the shelf component. And this is connected to your memory. And memory is of two types, RAM and ROM. And all these are connected by wired network called onboard or board level interface, or this embedded system is converted to the external world by wireless or wired techniques such as the communication interfaces provided. So thus embedded system is a combination of hardware and software, where the software is having a program to be written in the hardware. So this hardware together, its peripheral devices, sensors and actuators is doing a specific task. So embedded system is unique. It is unique and it is a microcontroller based real-time reactive system. So this covers our second unit. So we'll see our discussion on embedded system in further classes. Thank you.
This conference will now be recorded.